What's going on?
Okay, no, not here. Where? Screen recording, privacy.
Privacy settings. There we go. This recording.
Okay. This is screen recording. Yes.
Okay. Click here. Yeah, we're working on sharing the screen. So that's should be the last.
No, cancel.
Show Zoom is on.
Mm. Yeah, but it's not Zoom, it's Google.
Oh, you have to add. Then click add. Search for Chrome. Google Chrome. It's there before.
I know. It's weird. Why?
1A, 1O. Okay.
Open.
Yeah. Someone connected? Is
Yes.
someone connected or not?
Yes, now.
You see it?
Yes, now.
You see your desktop?
Yes.
Can you, let me see.
Now they see the same. The mouse.
Can you drag this? Try to drag it to the right. Oh, does it look good? Okay.
Okay, you can click it here. Okay. Start.
Can you see her still? Okay. He said he can see that.
You good?
Yeah.
Mm-hmm.
Okay, that's good.
Okay.
Yes.
All right, this should be good. Can you hear her and everything? Oh, well, there you go. All right, we should be good.
Yes. Yes. So, hello. My name is Natalia Maslenikova. Today, I would like to tell you about my current research, which is called Dynamics of West Antarctic Glaciers using remote sensing observations and ice sheet method models. But firstly, let me start from a couple of words about myself. I got my bachelor's degree with honors in chemical and biological physics in Novosibirsk State University, Russia. I also got a degree in pedagogy with honors in National Research Institute for Additional Education and Vocational Training in Moscow. Currently, I am the first year PhD student in geosensing engineering in the University of Houston. I also work as a research assistant in the National Center for Airborne Laser Mapping in the University of Houston, but before I worked as a laboratory assistant in the Institute of Chemical Kinetics and Combustion, governed by the Siberian branch of the Russian Academy of Sciences. I would like to acknowledge my advisors helping me in different areas of my research. Namely, my PhD advisor, Dr. Pietro Milillo, helping me with the remote sensing part, and Dr. Roberto Ballerini and Dr. Kalyana Nakshatrala helping me with the modeling part. I would like to provide some facts related to the state-of-the-art climate modeling. Here you can see the part from the latest IPCC report, which states there is a medium confidence in the representation of key processes related to surface mass balance and retreat of the grounding line in the absence of instabilities. However, there remains low confidence in simulation of ice sheet instabilities, ice shelf disintegration, and basal melting, owing to their high sensitivity to both uncertain oceanic forcing and uncertain boundary conditions and parameters. Before moving forward, I would like to explain the term that you will hear a lot in my presentation. The grounded line is a transitional boundary between the floating part of the glacier, which is called the ice shelf, and the grounded part of the glacier, which is called the ice sheet. On the grounded line, the glacier detaches from the bedrock and becomes afloat in the ocean water, forming a water-filled gap between the lower glacier surface and the bedrock surface. Here you can see the picture from the graph from another IPCC report. It shows the prediction of possible sea level rise in the year of 2100 for 5 different environmental scenarios. We can see that the thermal expansion contributes the most to the possible sea level rise. Antarctica and Greenland separately have relatively low contributions. However, the sum of Antarctica and Greenland contribution is comparable to the sea level rise due to the thermal expansion. If we look at the error bars, we can notice that Antarctica has the highest, introduces the highest uncertainty into the sea level rise prediction. Thus, investigation of Antarctica-related processes is important to us in terms of reducing this highest level of uncertainty. To calculate the sea level rise because of a glacier, we need to estimate the glacier mass balance, which is the difference of mass accumulation and mass loss. The mass increase happens due to the transformation of snow into ice, while there are 3 processes governing the mass decrease, namely the melting from the glacier surface, the melting because of the ocean water, and iceberg calving. In Antarctica, the temperature is so low, so there is almost no melting due to the sun. Ocean-induced melting and iceberg calving govern the mass loss in Antarctica and have approximately equal contributions. Ice flow modeling and monitoring is one of the most challenging environmental problems nowadays. And there are several reasons why. First of all, Antarctica is very big. You can see the comparison of the Antarctic size and the area of the United States of America. It means that if you want to monitor Antarctic changes and do it regularly, let's say daily, weekly, monthly, we need to collect and process a vast amount of data and do it also regularly. Also, we need to store this data somewhere. Antarctica have a very complicated behavior. In nature, there is not a single process governing the glacier behavior, but this behavior is a result of a complex combination of different parameters. And the example here is the mass balance, which is governed by 4 different processes. Also, there is still no clear understanding regarding the physical phenomena underlying the glacier behavior. And the example here is the grounding line migration, but I will tell about it a bit later. Also, the size of changes we want to monitor is very small, probably almost negligible in comparison to the size of Antarctica. That's why we need to obtain data of a very high spatial and temporal resolution. Grounding lines have a principal role in glacier investigations, for not only because they mm, uh, they control, represent their force and mass balances, but also allowed us to estimate the glacier contribution to the sea level rise. Also, there is no basal friction on the grounding line. The reduction of the basal friction towards the grounding line stimulates the ice flow towards the ocean and enhances the glacier calving process. Uh, on this animation, you can see that the mass balance, that the mass loss happens primarily along the coast of Antarctica. And there is one area where this mass loss is the most intensive. This region is called Amundsen Sea embayment. And generally speaking, this particular area determines the sea level rise of the whole Antarctica. That's why we are interested in investigation of this particular area. Amundsen Sea embayment, the area of Amundsen Sea embayment is approximately equal to the area of the state of Texas, and this area is presented by 5 glaciers, namely Pope, Smith, Thwaites, Pine Island, and Polar glaciers. In my research, in my research, I will use the information about the grounding line positions that was taken from the INSAR interferometric synthetic aperture radar data obtained by Cosmos SkyMet and Sentinel-1 missions. Also, I will use the information of glacier bedrock topography and ice thickness. Here you can see the demonstration of the BET machine. It's a NASA dataset where I took the information about ice thickness and BET topography. The ice thickness map was developed using Echo Saunders observations and the law of mass conservation. Bed topography map was calculated by the subtraction of the ice thickness map from the ice elevation data. Also in bed machine maps, ice thickness and bed topography maps comes with an error map. Grounding lines are invisible to the eye. However, because of their importance to Antarctica observations, lots of remote sensing techniques were developed. And in this research, I'm using interferometric synthetic aperture radar technique. Here, you can see the demonstration of Sentinel-1 mission. Data, so where I'm using the interferograms from this mission. So synthetic aperture radar is an active sensor which generates the portions of microwave radiation, points them towards the target, and measures the reflected signal. For a radar, as longer the antenna is, as higher resolution we get. That's why for a radar operating at 3 centimeter wavelength, to get a 10-meter spatial resolution, the length of antenna must be more than 4,000 meters. But it's impossible to construct such a long antenna and place it to the satellite. That's why the concept of synthetic aperture radar was invented. In this concept, one radar antenna, which is usually from 3 to 6 meters long, moves along the certain trajectory and frequently records the reflected signal and then processes this signal in terms of simulating a very long aperture, which is much longer than the real antenna size. Here you can see an example of a synthetic aperture radar interferogram. On the left, you can see the grounded ice, and the right part of the interferogram corresponds to the floating ice shelf. For synthetic aperture radar images were processed into this interferogram in a way to demonstrate the surface displacement, vertical displacement. The distance between two closest lines of the same color is called the interferomic fringe, and the distance between a fringe here is equal to it demonstrates the vertical surface displacement of half of the radar wavelength. In case of a 3 centimeter wavelength, the one fringe corresponds to 1.5 centimeters of surface vertical displacement. The grounding line corresponds to the most inner fringe in the interferogram, and the most inner fringe means the fringe that is the closest one to the grounded ice. And as a result of interferomic synthetic aperture radar interferograms is the position of the grounding lines that I'm using in the modeling part. It was so for a 1% surface, or 1% bedrock slope, a 1 meter sea level rise causes a 100-meter grounding line migration. However, it was recently observed that due to 1 meter amplitude tides, a grounding line migrates in several kilometers during one tidal cycle. The tides make the glacier shelf go up and down. It causes the forward and backward movement of the grounding line, and this movement is usually several kilometers, and it happens due to one tidal cycle, which is usually 1 day. The difference between the grounding line positions at the high tide and low tide is called the grounding zone. Current models that predict the long-term Antarctic behavior don't take into consideration the existence of the grounding zone. There were several attempts to explain physics of the grounding zone formation. Here you can see the list of them. And now let's look at them and see what this model and how this model explains the grounding zone formation. So the first model by Thomas and Bentley represents the bedrock and the ice as two solid materials, and there the grounding line position is calculated from the hydrostatic equilibrium for the floating part of the glacier. In this model, the grounding line is fixed. The second work by Sayan and Worcester improves the previous approach by introducing the stiffness of the bedrock. The authors use Euler-Bernoulli beam theory and consider a glacier as a beam. This approach is one-dimensional. It considers only the vertical displacement of the glacier mid-surface. This model itself doesn't reproduce the kilometric grounding zone. However, authors try to do it, but to make their model simulate a kilometric grounding zone, the authors assumed that the Young's modulus of ice is a function of a tidal cycle. The next model by Tsai and Goodmanson represents the grounding line as a crack, the grounding zone as a crack. They state that the grounding zone, that the crack opens at a high tide and closes at a low tide. This approach is also one-dimensional. It allows us to only to monitor the crack size, the crack length. However, it doesn't give us any information about the behavior of the whole glacier. The last model, the newest model by Stubblefield and others, uses a hydrodynamics approach to the explanation of the grounding zone formation. And using finite element method, the authors consider the ice as a flow of viscous liquid, and they managed to reproduce a kilometric grounding zone. Here you can see the demonstration how this model works. H0 here represents the thickness of the glacier. The authors looked at the movement of the glacier, the grounding zone formation, within 7 days. So this time here is the number of days. But in this model, authors fixed the bedrock slope. This bedrock slope is positive. However, in nature, namely, so in the area we're interested in, we can see reverse bedrock slopes. Exactly the existence of reverse bedrock slopes explains why this area loses mass so intensively. I improved this model by adding reverse slopes into the Stubblefield model, into the code that they provided. Currently, I'm checking the validity of this model and its ability to reproduce observed grounding zone width. On the right graph, you can see the blue dots represent the observed grounding zone width, while the yellow dots correspond to the grounding zone width calculated by this model. After checking the validity of the model, I'm planning to implement the variability of the basal friction coefficient. and calculate the ice flow velocity and check it and compare it with the observed ice speeds. After doing this, I'm planning to run several projections to analyze the long-term Antarctic behavior with the in presence of the grounding zone. And to do it, I'm planning to cooperate with the experts from the college, from the Irvine College and the, yes. So thank you for your attention.
I have a question.
Yes, sure.
Does the bedrock slope and elevation change when the ice above it melts and breaks off?
Repeat the question, please. Sorry.
Does the underlying bedrock,
Mhm.
does it change in elevation or slope when all the ice above it,
Oh, what do you mean? What do you mean change it?
like when it's no longer under all the weight of the ice?
It moves up or moves up. There's like a last
Yeah.
degree boundary.
Yeah.
It happens, but it's in a different time scale.
Oh,
Like it happens in like years and centimeters. Whereas if you remove the entire glaciers, yeah. So there is some rebounding, but you don't see those kind of things.
so it's not like the reverse slope is just following the ice as it breaks back?
No, the reverse slope is like bedrock. So what happens is that you have 2 kilometers of ice. We're laying that, and basically what happens is that once you melt that ice, there's less weight all of a sudden that has been there for 100 years. And then it goes up by centimeters. And you need other kind of measurements, but this is just, looking at the grounding lines, how big it is, because depending on how big it is, you have warm water infiltrating from the bottom, and then it melts. It could actually emits that you can reach further inland the glaciers and melt it from the bottom.
Thank you. Thank you.
Thank you.